Hello everyone, welcome back to Dedekind Cuts. So today we'll finally be taking a look at the definition of Dedekind Cuts, which is the name of this channel. To do this, we'll be taking a look at the real numbers in some detail. Specifically, we'll be defining what we mean by real numbers and look at three famous ways to construct it, of which Dedekind Cuts is one of the ways we'll be using to construct the real numbers. So without further ado, let us dive into the content of this video. Now, what does it mean to define the real numbers? Basically, the real numbers is a set of numbers put together, right? But just a set itself is not going to be very useful. We want certain properties that the set have. And by specifying the properties, we are essentially describing the real numbers. So I'm going to be putting out a statement that looks a bit difficult to understand at first, but I'll explain what it means. So the statement is as follows. There exists a Dedekind complete ordered field, and this is unique up to isomorphism. This set is called the real numbers. Now, if you are like me, the first time I read this, it just flies over my head. But what is this statement saying? Basically, we are looking for a set of numbers that satisfies certain properties. And what this statement is saying is that there is indeed a set that has that obeys these properties, which I'll explain in a minute what these three terms mean. But there is such a set that if we want it to obey these properties, we can find such a set. And in fact, there's only one such set, which is what this unique up to isomorphism means. There's only one such set, and this set is what we call the real numbers. So fundamentally, what boils down in the description of real numbers is the properties that we want this set to have. Therefore, it's very important for me to explain what these three terms mean, starting with the idea of a field. Okay, so this is the first property that we want our set to have. A field is a set of numbers where we define addition, subtraction, multiplication, and division in a way that obeys certain expected behaviors. So this is basically the broad idea. And to understand it fully, you will need to take a look at the list of expected behaviors, which I will not go through in detail because it will be a bit boring. But the key idea is these behaviors are things that would be natural, like society, commutativity, and so on and so forth. So if you like, you can take a look at the full list later on. But the whole idea here is we want our set of numbers to be not just the numbers itself, but be able to do operations between the numbers. Okay, so that's the first property we want. How about the second property? Now, we also want to be able to compare between two numbers. So this is what the second property is talking about. We want our field to be ordered, meaning that you can compare every two elements in a way that the comparison function obeys certain expected behaviors. So once again, the list of expected behaviors can be a bit dry to go over, but again, it's things that would be natural that you expect of a comparison function. For example, every element should be able to be compared to itself, like a less than or equal to a, and then maybe if a less than or equal to b and b less than or equal to c, then you expect a less than or equal to c. So these are the different sort of properties that we expect a nice comparison function to have. But again, the gist is we want to be able to compare between two elements. So that's the second property. And the third property we want our set to have, this one is a bit more abstract, so I'll explain it carefully. So now we already have an ordered field, and we want to add this third property. And this third property basically is Dedekind complete. What this means is that if we have this non-empty subset, and this non-empty subset has an upper bound, then it must have a least upper bound. Okay, what does this mean? So if you look at this set M over here, so this is a set that I'm now checking. And if you look at this number line, indeed, this set M have certain upper bounds, right? These are all upper bounds to the set. So the property of Dedekind complete is saying that whenever you have a set that have upper bounds, I must be able to find a least upper bound. A upper bound that is the smallest among all the upper bounds. Okay, if this still sounds a bit confusing, let's look at an example that is not Dedekind complete. So by the way, Q, the rational numbers, is also an ordered field. You can do your plus, minus, times, divide. You can compare between them. But what makes it not the real number is that it is not Dedekind complete. So here's why it's not Dedekind complete. Can look at one example, which is m equals to the set of rational numbers less than square root 2. So this set of rational numbers obviously have upper bounds, right? Like, for example, 3 is the upper bound of this set, because 3 is bigger than everything inside this set. So it's an upper bound. So it have an upper bound. Now, Dedekind complete means that this set, since it has upper bound 3, I must be able to find a smallest possible upper bound. But I cannot find a smallest possible upper bound. Well, 2 is also upper bound, okay, it's smaller than 3, but is 2 the smallest upper bound? No, 1.5 is also upper bound, is smaller than 2. Can I find an upper bound smaller than 1.5? Yes, 1.42 is an even smaller upper bound. Can I eventually find a smallest upper bound? And the answer is no, because remember, square root 2 is not inside your rational numbers. So you cannot say, oh, square root 2 is my least upper bound. No, because square root 2 is not a rational number. And no matter what rational number you choose as a upper bound, there is always a smaller upper bound to that. So this tells us that this Q is actually not Dedekind complete. And this is the missing ingredient that sets real numbers apart from the rational numbers. Okay, yeah, and this is our third and final property that we want the real numbers to have. So hopefully the definition, you get a slight understanding of what real numbers is, but the key question is, okay, I have all these properties, restriction that I put on the set of numbers. How do I even know that such a set exists? So in other words, is there a way I can construct R such that it satisfies the three properties that I've listed? So let's talk about a few ways that we can construct the real numbers. The first method is what is called Cauchy sequences of the rational numbers, or Cauchy sequences. Okay. So a sequence of rational numbers is said to be Cauchy if the numbers become arbitrarily close to each other as the sequence progresses. So before I give you the formal definition, I just describe it in a pictorial way. Okay, so I have a sequence of rational numbers, which is basically like maybe 1, then square root 2, not square root, 1, then 1.5, 1.3, 1.4, and so on. So this is a sequence of rational numbers. It's called Cauchy if the numbers basically start to become arbitrarily close to each other as the sequence progresses. And in formal terms, what this is saying is that for every epsilon greater than 0, there's a positive integer n such that for all mn bigger than n, we have absolute qm minus qn less than epsilon. Okay, this is very confusing if you are not familiar with this language, but basically this is saying no matter the threshold that I'm given, as long as I go far enough in the sequence, so this is the part that says once I go far enough in the sequence, I'm guaranteed that my numbers in the tail of the sequence is all below, have a difference of below the threshold. Yeah, so roughly speaking, this is what this formal mathematics is saying. And even more roughly speaking, it's just saying the numbers become arbitrarily close to each other as the sequence progresses. Now, why am I even looking at this idea of a Cauchy sequence of rational numbers? So the key idea here is, take for example square root 2, right? Square root 2 is not on my line of rational numbers. But what I can do is I can sort of fill in this gap by taking a sequence that goes towards that gap. So I don't have square root 2, but I can take a sequence of rational numbers that approaches towards that gap. And then I say that sequence is my definition of square root 2. So in other words, the whole idea here is I'm going to let S be the set of all Cauchy sequences of rational numbers. And this sounds like, okay, now I can fill in all the gaps, but there is one problem, which is that there could be multiple sequences that end up going towards the same destination. And well, the simple solution is you just bundle all these sequences as one real number. So you say all these sequences that head towards the same destination, I'm going to define all of them as equivalent, and they are all going to represent this single real number. So in other words, what do we mean by two sequences heading towards the same destination? Well, we say two Cauchy sequences, Pn and Qn, to be equivalent if for all epsilon greater than 0, this is again our threshold, there's a positive integer n such that if you go far enough along the sequence, the difference between the two sequences is less than the threshold. Okay, so with this definition of what we mean by two sequences heading towards the same definition, we can now say that the real numbers is basically the equivalent classes of S. So we take all possible Cauchy sequences. Whenever two of them head towards the same destination, we treat it as the same real number. Okay, and by performing this equivalence relation, whatever that is left is all the real numbers. So for example, square root 2 is inside this definition by taking any sequence of rational numbers that head towards square root 2. Two different sequences that head towards square root 2, they both are considered to define the same real number of square root 2. Now, by the way, the rational numbers themselves are also included inside. It's not just the gaps between rational number. And do you see how? Well, this is because if, let's say we have a rational number q, then we can look at the sequence q, 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 q. This is a valid sequence because all these are rational numbers. And indeed, this is obviously Cauchy because the gap between terms obviously gets arbitrarily close as you go along the sequence because the differences are like 0, right? So this is a Cauchy sequence. The equivalent class of this sequence is going to represent the real number q. Okay, so very nice. We now understand how the real number is constructed. Now, of course, you need to check that this definition satisfies the three properties that we set out for real numbers. But I'm not going to check through them one by one. I just want to give you a flavor of, for example, how might you define addition between two real numbers if I define real numbers like this. Well, basically, let's say we have a real number r and a real number s. Now, by definition of our real numbers here, it must be represented by some Cauchy sequence of rational numbers that head towards r, right? And same thing for s. It's basically a Cauchy sequence that sort of heads towards s. And the way I define addition is that r plus s would then be the real number that is represented by this Cauchy sequence. Yeah, so there's a bunch of things to check, but just to give you a flavor of what addition will look like with this definition. Okay, this is method 1, but by the way, method 2 is just a special case of this, and it might even help you get a better understanding of method 1. So let's talk about decimal representation. Now, a sequence of decimal expansion is basically a Cauchy sequence in rational numbers because decimal expansion by here, what I mean is you write the integer part, then you start adding one decimal point as you move along the sequence. So this sequence here is clearly Cauchy because, well, as you go far enough out in the tail, the differences start to shrink and you can show that the terms start to get arbitrarily close to each other. Okay, so I'll leave, if you want to do the formal checking, I'll leave you to do so, but intuitively this should make sense. And so what we can do, previously we said the real numbers is basically you take the set of all Cauchy sequences and then you take the equivalent classes, right? Now I can just, because a decimal expansion is basically a Cauchy sequence, so I'm looking at the subset of Cauchy sequences now. And so I basically can do the same thing. I let S be the set of all decimal expansion, and I define the real numbers to be the equivalent classes of S. Yeah, so this might be the definition of real number that you might be most familiar with. And in fact, here is a fun interpretation of fun fact. If you understand this definition of real numbers, so you might have seen certain memes saying that like 0.999 equals 1, but you might not really understand why this is the case, right? And with this definition, you can now see that this is actually a mathematically correct statement, because basically 0.999 is basically talking about this decimal expansion sequence, and 1 is basically talking about this uh, decimal expansion sequence. And by definition, these two are actually equivalent, because uh, the gap between the terms get arbitrarily close. So these two are actually in the same equivalent class. And because real numbers is defined up to equivalent class, these two actually reflect the same real number. Yeah, so this is a neat little realization if you look at this definition of the real numbers. Okay, and last but not least, Dedekind cuts. So to some extent, this might be I think it's a simpler way of understanding the real numbers. So let's take a look at what this means. Okay, basically, Dedekind cut of the rational numbers is a way to cut the rational numbers into two non-empty sets A and B, such that every element of A is less than every element of B. A contains no greatest element. What does this mean? Basically, I want to cut the rational numbers somewhere and then into a left side and a right side. So my left side will be A and my right side will be B. And basically, this is what the first condition is saying. Every element of A is less than every element of B. So my rational numbers, I want to cut it into a left side and a right side, where left and right are non-empty. So for example, over here, I have made a cut at square root 2. Now, of course, square root 2 is not a rational number, so it doesn't make sense for me to say I cut at square root 2, but basically what I'm trying to say here is I let A be the set of rational numbers less than this thing called square root 2, and I let B be the rational numbers bigger than square root 2. So imagine for a second you have real numbers in the background. You know what are the rational numbers that are less than square root 2 and bigger than square root 2. I partition it into this way. Then now I can delete away my understanding of real numbers. I basically have these two sets here, and it obeys this property. And also it obeys this property. A doesn't have the greatest element, because you can get arbitrarily close upwards towards square root 2. Now, why is there a need to include this second property here? It's because let's say instead of cutting at this gap here that is going to correspond to square root 2, I have another Dedekind cut that cuts at 1. So 1 is not a gap, right? It's a rational number. But if I cut at 1 and I into a left side and a right side, there's two ways I can do the cut, right? Depending on where I put the number 1. I can put the number 1 to the left side into A, or I can put the number 1 to the right side into B, and it will satisfy this first bullet. And that would be problematic to have two different ways of cutting at the number 1, because I want there to be only one real number that means 1, right? So this second property resolves this by forcing the number 1 to be with B instead of A. Because in doing so, then yes, now there's no greatest element for A. Whereas if you put 1 into A, then A has the greatest element, which is the number 1 itself. Okay, so basically, if I cut at a gap, I'm going to get a new, like an irrational number. Then if I cut at an existing rational number, then I'll just get the rational number itself. So now, by the way, I can just describe a Dedekind cut by describing the left side, because the right side is the complement. So from now on, when I describe the Dedekind cut, I will just tell you what's the left side. Okay, so anyway, the real numbers then is the set of all Dedekind cuts of Q. So it's very intuitive. It's basically all ways of cutting the rational numbers into the left side and right side. So as I explained earlier, if you cut at a gap, you're going to get a irrational number. If you cut at an existing rational number, you just get the rational number itself. Yeah. Once again, you will need to actually check all the different, like the 3 properties that we demand of the real numbers, which will be a bit tedious for me to go through. But to give you a flavor again, how might you do addition with this definition? So this definition now here tells us the real numbers is basically a way of having a left side to the rational numbers, right? So let's say R here is a real number, but it's also corresponding to a set, the left side set of a rational number. Then S again is another left side set of the rational number. Then to define R plus S, I'm just going to define this set here. So I take all possible sums of something from R and something from S. And this thing you can check correspond to a left side set of the rational number. So this corresponds to a certain Dedekind cut and therefore a certain real number. Yeah, so, and this will be the definition of the sum. Yeah, so this is a bit of a special video. The mathematics is a bit, or rather a lot more abstract in this video. So what do you think of videos like this? If you find it fascinating, even if it's a bit difficult to understand, do let me know in the comment section below, and I'll see you in the next video. Thanks for watching.